In this lecture, we look at a new characterization of absolutely continuous functions that will be useful later when discussing theory of Newtonian Sobolev functions. The theorem says that a function defined in a compact interval in R is absolutely continuous if and only if there is a integrable function on AB so that integrating g gives us f. So we see that this direction was already discussed in lecture 2 because we saw there that actually if f is absolutely continuous, then f prime does exactly what g is claiming to do here. So this equality, the fundamental theorem of calculus, will be what we want to start. So here we're looking at the converse, that if you start off with an integrable function, so all we need to show to prove this converse to this, we need to show that this function defined by this, that f of x, so we are assuming that g is L1 and that star holds, so these are part of the assumptions. We need to prove that f is absolutely continuous. So we need to show that this f such defined is absolutely continuous. We don't need to show that f is equal to that. If you read the statement carefully, this is part of the assumption in the converse direction. That we need to show that this function defined this way, which is well defined because g is in L1, so for any x, this quantity integral is well defined, and f of a is just one quantity we add. So this will be absolutely continuous. So is absolutely continuous. So the proof of this follows from what is actually known as absolute continuity of integral. Integration is an absolutely continuous operation in the following sense. So absolute, this is famously known as absolute continuity of integration or integrals, which is correct in much more generality, but let me state it for Rn. So if you have a function in L1 of Rn for any n, then for every epsilon positive there exists a delta positive such that for any measurable subset of Rn, so for any measurable A, the following is true, that if Lebesgue measure of the set A is less than delta, then integral of absolute value of f over A against the Lebesgue measure will be less than epsilon. So this is saying that if you integrate over a small set, then definitely the integral will be small. This is an obvious claim if f is a bounded function, because in that case this integral will be less than or equal to maximum supremum of f times measure of a. So if we make this a small, then this becomes small. However, the interesting case is when f is actually unbounded. So we know that unbounded functions can nevertheless be integrable. So they can have a blow up, but still be integrable on Rn. So Rn is flat lying down, and this is the function f. So what this theorem is saying is that you cannot concentrate the integral too much along just the blow up. So if you take a small set here, although here f is really large, the compensation is in favor of the smallness of the set, so that the integral will be small even though f does blow up to infinity. So the set wins. This is a famous fact about integrals, and you can find its proofs, some elementary, some using other facts from about integrals like monotone convergence, but overall it's very simple fact. And the another nice thing about this is that we have no restriction on a other than just being measurable. Okay, now what does this have to do with the situation in hand with absolute continuity of the function? We want to show that this function is absolutely continuous. Then what can we do? So we take a partition, obviously that is the proof. Let say ti, I like j actually as an index, jij plus 1 for a okay, so these are subintervals, finitely many, be a finite collection of subintervals in AB. That's, we want to just follow the definition of absolute continuity in the sense of functions. We must bound, so let me not write too much words, let me just get to the calculation. So I want to put a bound on f of tj plus 1 minus f of tj, absolute value, and then summation over j. But this is summation over j. If I go back to this equality star, this one here, so a bilinearity of integral, the inside is nothing other than integrating from tj to tj plus 1 of gt dt. Okay, and then if I put that absolute sign inside the integral, I can only improve this integral's quantity. So let me put the absolute value into here. And then, of course, these are disjoint, non-overlapping intervals. That's why they can add up here. So this will be integral over union over j of these non-overlapping intervals. So we just take them as a set, right? And then you integrate gt, absolute value, dt. Now, to show absolute continuity, we need to show that if the summation of, so by absolute continuity of integrals for every epsilon positive, there exists a delta positive such that if measure of this union, let me put Lebesgue measure 1, L1 measure of the union of these subintervals, which is summation over j of just difference tj plus 1 minus tj. If this one is less than delta, then this integral, the last integral here, let's give it the name, well, not the name, I follow my PhD advisor giving hearts and stars to things. So then this heart is less than epsilon. So for every epsilon, there exists such delta by absolute continuity of integrals. Here, g is integral of absolute value of g over the whole interval ab is finite. And this is exactly what we have for definition of absolute continuity. We just showed that if this summation is less than delta, then this summation of values will be less than epsilon, no matter where you take these non-overlapping intervals, which by definition, so the function f is absolutely continuous in the sense of functions. Right, this f is absolutely continuous because this inequality is for f values. And that completes the reverse side of this. Of course, as a remark, let's see that in retrospect, we see that from the previous lecture 2 characterization, we know that now that f is absolutely continuous, it is differentiable almost everywhere, and that claimed inequality holds with f prime. So if you have two competing functions satisfying the same equality for all values of x, then these should be almost everywhere equal functions. Of course, f prime, well, this g cannot be any g. G is actually equal to f prime almost everywhere on A, B. So the nice thing about this characterization is a priori you don't need to assume that the equality holds with f prime. If it holds with any g, then you know it's absolutely continuous, and then you know that the function is differentiable almost everywhere, and then you know that that g has to be equal to f prime. And the reason I actually made this a separate video is that when we talk about Newtonian Sobolev functions, we will say that there exists a Borel function along this curve, so that when you look at the value of the would-be Sobolev functions, so u of gamma of t2, gamma is the curve in your space x, and then for u, which is a function from x to r, you would want the behavior on curves to be governed by this. So u value at different points of this gamma curve, you will want that to be less than or equal to integral of a non-negative Borel function along this curve. So we see here that you won't have equality but an inequality, but based on the same proof above, this would follow. This would mean that, so this is for every t1 and every t2. From this, exactly like the previous proof, if this integral, so this is only from the segment from t1 to t2, let's say, that part of the graph. But so if on the whole graph this is finite, then rho is integrable, and from the same proof as above, it follows that u is absolutely continuous on this curve gamma. So the inequality here is sufficient, and that's why this characterization of absolute continuity is quite effective, although at the end of the day it ends up for this g just being the derivative. Okay, so we will talk, don't worry about this last part. Of course, we haven't formally talked about Newtonian Sobolev functions yet, but now we have built the first important background necessary to understand them, which was the notion of absolute continuity. So in the next video, we can begin talking about absolute continuity along curves, because so far we only have talked about absolute continuity of functions defined at compact intervals of R1, but we want to get rid of that, and we define integral and absolute continuity along all curves in all spaces. So gamma, it will be a continuous function into a metric space. And once we're done with absolute continuity, we will introduce the notion of almost every curve, and putting these together will give us the Newtonian Sobolev space. I don't want to rush things, as I have promised, and try to bring out the details and subtleties, and you will help me immensely if you put your questions in comments sooner than later so that I can incorporate them into my future lectures. Thanks a lot for watching, and please again, if you haven't subscribed to the channel, to give me some more thumbs up. Thanks a lot.